Okay. Sorry for the delayed start of the meeting. If it's not one technical difficulty, it's another. At least we had a new one tonight. So I apologize for that, but we're going to get going after all. As probably most of you know, I am Charlie Nielsen, the president of this little band of astronomy enthusiasts. We have some other officers in the room, and I think some on Zoom also. We'll get some reports from them later on. However, I don't think you came here just for that. You probably mainly wanted to hear from Timothy Campbell. So, as tradition would have it, we always have our guest speakers speak first. So, if people didn't want to stick around for our highly entertaining business meeting, we might let you escape. So, tonight's guest is Timothy Campbell, and he is a NASA JPL Solar System Ambassador. It turns out one of our longtime club members and a past vice president, Don Foey, saw Tim talking at the Ford Amateur Astronomy Club Astronomy Expo last spring, was quite impressed, and asked him if he would come and do a presentation for us, and we were very pleased when he said yes. So Tim has always been interested in space. He was inspired from watching the Apollo missions as a young child, but he really got hooked when he saw Saturn's rings through a telescope. I think we all had that experience, huh? Well, you can still find Tim looking through telescopes. These days, he wants to know how these things work. So cool, geeky science experiments are often added in for extra fun. Tim is a past president and active member of the Ford Amateur Astronomy Club here in Michigan, and is also a planetarium operator and presenter at Henry Ford College. Tim does numerous outreach events and talks both under the night sky and indoors, as we have them today. But you might have noticed in my meeting announcement, I said that Tim was actually going to join us by Zoom because he had some difficulty stuff. And that's still true, but it just is a demonstration of our really good technology and holograms. We present him in virtual form. If anybody's buying that. With that, I give you Tim Campbell.
All right, thank you. Okay, get this clip back in. All right, you guys can hear me okay?
Yes, we can.
Yes.
I'm seeing this meeting is being recorded on the, I think it's on your.
All right, let me see if I can adjust this. That'll be pretty good. You can turn me off if you don't want to see me. All right, so as was mentioned, I'm a solar system ambassador, and the presentation that you're seeing was actually, I would say the foundation, the core of it was put together by the Space Telescope Science Institute. So as a solar system ambassador, they look for people that will do outreach on various topics. And they said, hey, we're looking for people that will do web talks. So I raised my hand and said that I would. So instead of just a bunch of pretty pictures, they actually trained me on what the pretty pictures mean. So you'll get a little bit of an explanation of it. And I'll take you through. There's a lot of slides in here that I've turned off. What I have not turned off is, I'll tell you up front, 52 slides, which is an insane number of slides to put in a presentation. But I promise I will go very quickly through many of these slides. Some of them will only appear for seconds. Some of the important ones I'll leave up for a couple of minutes before we go on. But I think I can make it. I've done this talk a number of times before. I do keep refreshing it. The core of the presentation was actually done for the release of the actual first images. I'm getting an echo of myself. There we go, I muted it. It was recorded actually for the release of the first images, but we do quarterly updates on it. And excuse that, there we go. We get quarterly updates on it. And so some of the latest images are actually in here. Images that are only maybe a month old are in this presentation. So with that, let's get started. The first thing I want to talk about is the difference between Hubble and Webb. So Hubble is the other great space-based observatory that we have. But you can see here I've got an image that kind of gives you a scale of how big Hubble's mirror is compared to Webb's mirror. And you can see Webb's multi-segmented mirror is considerably bigger than Hubble's mirror. Hubble is primarily a visual spectrum image. It can touch a little bit into the UV and a little bit into the IR, but not much. It is primarily a visual telescope. Webb, on the other hand, is entirely an infrared telescope. It does not see light in the visible light at all. Every image you've ever seen from Webb has to have its color values translated so that we can actually see. because in the actual data that it's seeing, humans would see absolutely nothing. But it's not just bigger because we like bigger and it's newer. It's bigger because when you start going after longer wavelengths, you fit fewer of those waves across the width, the aperture of the mirror. If it were only the same size aperture as Hubble, you would actually see lower resolution images out of the Webb than you see out of Hubble, because Hubble is looking at wavelengths that we measure in the visible spectrum that we measure in hundreds of nanometers. Webb is measuring in micrometers, right? So micrometers is a million to a meter, and a nanometer is a billion to a meter, right? So we're 3 orders of magnitude difference in our wavelengths. All right, so I wanted to talk a little bit about the instruments. Whoops, let's go back here. I didn't mean to do that. There we go. I want to be able to annotate on this one. All right, so there are 4 main instruments that you're going to hear me talking about over and over again, and I wanted to call your attention to them. So the first one is up here is the NIRCam. NIRCam is the near infrared camera. So that's the camera that most of the pretty pictures you see out of Webb were taken actually with the NIRCam. But we also can image in the mid-infrared. And so if the near-infrared camera is called NIRCam, of course you all know that the mid-infrared camera is called MIRCam, except it's not. It's actually called MIRI. And you'll think, why is it called MIRI and not MIRCam? It is mid-infrared instrument. I thought it was near-infrared imager. It's not. It's mid-infrared image instrument. And that's because these things were made by different people, different teams worked on it, and they came up with different names, and they didn't force it to have a consistent naming convention. So those are the 2 cameras. There are also 2 spectrographs on the telescope. The first one up here on the left is called NIRSpec. That's a really cool one. And what that does, this is a first of its kind spectrograph. So you've all probably seen images of the Hubble Deep Field image, 5,000 galaxies in an image only 2.4 arc minutes across. If you wanted to do spectroscopy on those galaxies, you would have to point at one galaxy, take a spectra, measure it, translate the results, find out what it means. Pick another galaxy, measure it, get the results, find out what it means. And with 5,000 galaxies in an image, you realize you could be there a while. So the first of its kind that NIRSpec has is this thing called a microshutter array. It is actually able to take the spectra of tons of objects in the image all at the same time, which is really cool. So when we get images, you'll see I'll show you the first image you'll see is the deep field image that Webb took. They're actually able to find out, what has the biggest redshift in that image very quickly from the data. And then the last instrument that they have is this thing called FGS NIRIS. FGS actually stands for Fine Guidance Sensor. We're not so much worried about that, but NIRIS is what we're more interested in. That's the Near Infrared Imaging Slitless Spectrograph. NIRIS can only take the spectra of one thing. So it's not like the microshutter array of NIRSpec. But what NIRIS can do that NIRSpec cannot do is NIRIS can detect molecules in planets' atmospheres or in molecular clouds down to the parts per million level of sensitivity. So it is incredibly sensitive. And later on, I'll talk about why that's really, really cool. So those are the 4 images, or the 4 instruments, I'm sorry. So let's move on. So I'll talk a little bit about where is it in the orbit. So it's at this place called the L2 Lagrange point. So there are 5 Lagrange points. It's at the L2 point. It's roughly in line with the Earth, about 1 million miles away. There's a problem with orbits when things are not at the same distance. So we're roughly 93 million miles from the sun, and we take 365.24 days to go around. Actually, that's not quite true. That's a tropical year. That's not actually, that actually does not compensate for precession, 26,000 year precession cycle. But let's just say it does, right? So I'll keep it simple. But in one full year to go around 365 days, Webb is 1 million miles farther away. So if you think about the planets, Mercury, 88-day orbit, Venus is 224-day orbit, Earth is 365-day orbit, Mars is about 2 years, Jupiter is about 12 years, Saturn is 30 years, right? The farther out you are, the longer you need to do a lap. So we should, with Webb being 1 million miles farther away, it should not keep up with Earth. We should be slowly, gradually losing it in the dust, and yet we aren't. And so here's the magic of why that is. So if you want to understand how simple Newtonian gravity works, you need to know 3 things. The first 2 things that you need to know are the masses of the 2 objects you care about, in this case, the sun and the Webb. You also need to know what's the distance between their centers of mass. So we call that r. And then you drop all that into an equation. And in the equation, it's the mass of object 1, m1, and the mass of object 2. You multiply these 2 things together, and you divide it by not just r, but the square of r. And that's all you really need to know. Now, there is this nagging little thing out here on the side called g, which is that's the gravitational constant. It's 6.67 times 10 to the minus 11. So, move the decimal point 11 points over, and you can see there's a lot of zeros before you get to 667. So it's a really, really, really small number. But actually, you can ignore the g. The g is a scaling factor. It's like, I want to convert centimeters into inches. I got to have a scaling factor so I can. So if you want to be able to compare this force to other forces, you need a scaling factor. That's the only reason it's there for. So really, forget about the g. It's just those 3 things. That's all you need to know about. Well, here's where it gets cool with the Lagrange point. So we still have the sun, and we still have Webb. And we have a distance between them, r. And we drop the same equation that you saw before, except they've changed the subscripts to m sub sun and m sub Webb for reasons that are about to become apparent. But you also get to do the Earth. And so I add in the mass of the Earth, 6 times 10 to the 24 kilograms, and the radius between that, or between the centers of mass. And I drop the equation down there for that equation. And then here comes the really complicated part. Are you ready for this? You put a plus sign in the middle. Webb feels the force of gravity from both the sun and the Earth at the same time. And you add them together. This creates the illusion to Webb that it is orbiting a star that has more mass than it actually has. And to be able to maintain a stable orbit 1 million more miles away from a star that has more mass, it needs to do that orbit in 365 days. And so that is why Earth and Webb can fly in formation without us ever leaving it in the dust. Now, it's kind of a saddle-shaped gravity well at that point. If it gets a little bit too close, r starts shrinking, and of course you're shrinking it by the square of r, and the illusion of the amount of mass goes up too much. And so Webb now has to move faster. That's no good. Or if it's a little too far out, the gravity drops off too much, and now Webb has to move a little bit slower. So you got to keep that in and out distance at the right magic spot. But as long as you do, you get the stable orbit. Here, just for reference, is where the other Lagrange points are. We do use them. So we've got satellites at L1, for example, monitoring the sun. Discover comes to mind. And there we actually subtract the mass of Earth from the mass of the sun. There's one on the opposite side of the sun. And the Trojan asteroids of like Jupiter has Trojans, lots and lots and lots of them. I think they did discover that Earth has at least one at the L4 and L5 points. And those are actually very stable gravity wells. All right, so getting on to the infrared light. Why study the infrared light? So here's the problem that Hubble has, is that as light comes across the universe itself is stretching out. It's getting bigger. So if you think of a slinky and how many coils you have in the slinky, and the slinky is moving at the same speed, but you're stretching the race course that you're traveling across, the spacing of the coils is increasing, if you want to think of it that way. So it's stretching out. So even light that was emitted from first galaxies will have stretched. Even if it was emitted in the ultraviolet, it will have stretched so much that it will have stretched completely. We talk about redshift, blue light starts looking more like red light. Well, it will stretch so much that it will stretch all the way off the visible spectrum completely. And now that renders Hubble blind to that light because it can barely see just a tiny bit of infrared light for Hubble. So they said, we need a telescope that can handle much longer wavelength light, because we can calculate how much that stretch should be. And that is why they built Webb as an entirely infrared telescope. So I've got a comparison chart. Hopefully this is showing up well on the screens. Some of the screens that I use, it washes out and you can't see the difference, but we've got a shaded area of the graph here showing Hubble here. And you can see that Hubble is basically here in the visible light, getting the full, but it sees a little bit into UV and it sees a little bit into IR. Webb, on the other hand, it sees the entire top of the IR spectra, and it gets down well into the mid-infrared. It doesn't get into the far, far infrared. It doesn't go all the way down there. But hey, Spitzer does. So Spitzer gets into that part of the spectra. So we've pretty much got it covered with these instruments out there in space. And that's why we did it. So when we go on to what we're going for, here in this drawing, let me see if I can annotate this again. So there's this spot here. This is where so we've got the Big Bang, right? And then we've got this orange section. That is when the universe was basically not transparent to light. Everything was ionized. The universe is a plasma, right? The sun is a plasma. You cannot see through the sun. The sun is not transparent. You can't see through a plasma. But something like 380,000 years later, it cools down enough that electrons can finally bond to atomic nuclei, and it's no longer a plasma, and it becomes transparent to light. They call that the last scattering surface. They also call it the epoch of recombination. I always thought recombination was a terrible name because it presumes that the electrons, they were once combined and then they were split up and hey, they got back together again. It's like, no, it's actually the first time they got together, but we called it recombination anyway. And then the universe is just dark. Stars have not yet formed, but the universe is transparent. So they call it the dark ages. And then there's this purple spot here. And they call that the epoch of reionization, which is a complicated way of saying stars were born. Stars ionize the gases and the electrons get ripped away. And now you see stars as a glowing ball of plasma in the sky. And so you don't really expect to find stars in the dark ages, but you do actually at the epoch of reionization. And so they designed the Webb to see all the way back to that point, the epoch of reionization. And you can see here, I've got Hubble, and you can see that that's about 1 billion years after the birth of the universe. And that's about as far back as Hubble can see, but Webb can see back farther. So if we want to see what was going on and learn more about how it all got started, we need something that can do a better job than what Webb can do. And that's why we have that telescope. Okay, so there are, I want to say 5 primary missions. It's from memory. You can count on me, and maybe I got the number wrong, but I think it's 5. Okay, so we want to crisscross the early universe and see how these first stars and galaxies are actually forming. We expect the first galaxies to be rather disordered. And then I say we want to find samples, and I say, this is the thing that your mother did to you. Oh, maybe your mother didn't do it to you, but they have the birthday picture. Oh, let's take a picture of the kid every single year of their life. And you do this, and you, as an adult, you get the photo album, you're going back, and all of a sudden you find out that there are no pictures of you before you were 5 years old. And your mom, why are there no pictures of me? As my friend Liam says, because I was an ugly baby. But I usually shoot back at them, and it went downhill from there. But you could say, well, they hadn't invented cameras back then, or come up with whatever excuse you want. But the idea is, well, what if we had something that could actually go back that far? And so that's one of its missions. The other thing is to be able to dissect a black hole. So one of the problems with trying to see black holes, especially these supermassive black holes, is we find them in the cores of galaxies. So they're the galactic core, and the stuff is covered in dust. So when you use a visible wavelength telescope, you really don't see anything. But if you have an infrared telescope, the cool thing about infrared wavelengths is the wavelengths are so long that they're substantially larger than the dust particles blocking the visible light view. So they just wrap around the dust and head on through it like it isn't even there, pretty much, or maybe it's just slightly milky. But it makes dust largely transparent. In fact, in this image, you can see the image on the left was actually taken by Hubble, and the image on the right is the very same object taken by, I got a typo. What do you know? It says infrared light by Hubble. Actually, that might actually be Hubble, but that's because Hubble can do near. I thought that was a Webb image. But that's an example of what you get by going to infrared. You can see the gas clouds are milky a little bit, but you can largely see through them. We also want to be able to detect the molecules that we can find in these star-forming regions. And that's why I mentioned we have that thing called NIRISS, the slitless spectrograph that can see what's out there down to the parts per million level of sensitivity. To be able to do that, we want to be able to re-examine things in our own solar system. So we've got a little bit of science there. This is not the original image that NASA gave me. I've actually substituted this, but this was taken by Webb. Do you notice anything peculiar about this image? Something in this image that you've never seen before, other than the fact that the colors look wonky.
The ring?
The rings, yeah. Here's an actual photo of the rings. So I remember when the rings were first discovered, and they were like, well, we're pretty sure there's rings. Well, why are you pretty sure? Well, we noticed the star blink out a certain time period before it gets to the edge of Jupiter. And then on the far side of Jupiter, it blinked out again. Well, and it exactly the right spacing. So they said, we think there's, some debris there blocking it, right? Not that we ever had a photo. Well, we got a photo. So there you go. All right. The other thing that we can do with this is do direct imaging of exoplanets. Almost all exoplanets that you've ever seen or read about, not all, but oh my gosh, this is the lion's share, are done by this thing called the transit method to discover the exoplanet. So let's talk about the transit method. You are a space alien. You live on some star in the Milky Way galaxy. You're pointing your instruments at our sun, and you want to see if you can detect us. Okay, you're all familiar with that imaginary line in the sky that we call the ecliptic plane. From Earth, the sun appears to be a half a degree across from edge to edge. You have to live on a star, or you have to live on a planet, not a star, orbiting a planet that is within a quarter of a degree either side, so a total half a degree of the ecliptic plane. If you live anywhere else in the universe, you can't see us, right? Not using that method, you can't. So the direct imaging method, considerably harder to do, but it lets you, and yet the bulk of our stars are discovered by this transit method. So extrapolate that with what you know about the ecliptic plane, and imagine how many exoplanets that are out there that we've just never found yet. We're basically finding, I hear these guys, we don't think our solar system is normal. We think most solar systems have massive planets in them, and it's not normal to have small planets. And I said, there's a little bias in the data because the way we find these things, we're not using the techniques that let you find the small planets. So of course, that's all we find are the big ones that transit. All right. I did mention NIRISS and being able to decode the atmosphere of a planet. So when I talk to audiences, and oh gosh, I got to be careful when I bring this up. There are, for any molecule that you can have, physicists can think of ways that you can form that molecule. And some of those processes that will form up molecules do not require biology. It can happen in other ways. But there are some molecules that form that the only way we can think of is to involve biology. So the question is if you detected the presence of one of those, that second category in the atmosphere of a planet, would you have found life? And this is where I hit the brakes and say, well, wait a minute, it's easy to get carried away. You definitely found something really interesting, because maybe what you found is a new way for an abiotic process to form a molecule that does not require life. Maybe you found that. That would still be very interesting. Maybe you actually did find not directly the life, but maybe you found a marker for life in the atmosphere. Either way, it's a really interesting discovery that you have. And for the first time ever, we actually have a telescope and a spectrograph with the sensitivity to be able to do that kind of work. So that to me is just mind-blowing in itself. Okay, so I talked about the various kinds of things that Webb was designed to do. So with that, let's actually get into the data. And this is the first big reveal. This is because the first time I gave this talk, nobody had ever seen the images yet. All right, so here's the first image. And this is Webb's deep field. And notice up at the top, I'm going to put this in annotation mode. Notice up at the top, I have this name SMACS 0723, which just rolls off the tongue. But that's actually the shortcut nickname that we give it. The real name is down here. If I can underscore this, I didn't do a good job. SMACS, I'll just kind of highlight it. SMACS J0723.3 minus, not dash, minus 7327. And you might wonder, where do you come up with that name? Well, do you see the next line that has right ascension? Oh, look, 7 hours, 23 minutes. Well, you saw J0723, and there's 7 hours, 23 minutes, 13 seconds. Declination, minus 73 degrees, 27.4 minutes. And you see the 7327. That's how they come up with the name. So the name tells you where it is. Where was the telescope pointing in the sky? And that's where they pointed. And so with minus 73 degrees declination, deep into the southern hemisphere, can't see it from Michigan. But there you go. And this was the first deep field image. The cluster that they're imaging has a z-value of 0.39. It translates to about 4.6 billion light years away, which is kind of cool. And then what I wanted to show you was, should zoom in for you. And remember I told you we have that little thing called near infrared spectrograph with the microshutter array that can do lots of things. So it found this interesting dot here. And when they take the spectra of that little dot that I've circled, they get a z-value of 0.95. That was the most distant thing that they had noticed up to that point in this image. And I've circled it for you. That translates to 13.1 billion light years away. So that is beyond what Hubble would have been able to see, but Webb can see it. I should probably call your attention to the diffraction spikes. So you see the diffraction spikes here. It's mostly you're going to see 6 sides. So let me just change the color. So you got 1, 2, 3, except so you got 6 points. But you've also got this little skinny one here. The edges of each hexagonal segment is causing those bright diffraction spikes. But there's also the struts that are holding up the secondary mirror in front of the telescope. And that is creating the really dim, completely horizontal one that you see. So generally, when you see one of these largely 6-pointed, except kind of 8, pointed star-like structures in your image, that's not in the deep universe. That's a star in our local galaxy photobombing the image, mostly, not always though. So here's the same image, but this time I'm doing a comparison showing you the difference between what the near-infrared camera took versus the mid-infrared camera took. And you see they look quite different in terms of the data that you can see there. But this is something else that I kind of wanted to point out. And I'll spend just a minute on this. I get this question a lot. Now, you all are an astronomy club. Some of you probably have advanced education in the field. And so a lot of this you probably take for granted. But when I talk to people at schools and libraries, these are things they don't know. So they say, how are they giving us the age of that thing? Well, we're giving you is not the age of the object. We're giving you the age of the light that was emitted from the object. The object could have been, much older, but this is when the light finally made it to us. So we're doing the age of the light. Now, here's the same image, but we've called out 4 different structures in the image. And the first structure I'll point to is this one here. And you can see they've got a little inset blow up of it here. But this is the part that I wanted to show off, which is you see this spectra here, and you can see there's a red spike, 2 little spikes that we've shaded blue for oxygen, and then another hydrogen spike. That's your hydrogen beta and hydrogen alpha emission absorption line in the Balmer series for hydrogen spectra that you're seeing. And you're also seeing the oxygen in there as well. So when you see these, you say, oh, that's hydrogen gas, great. But now in the next image down, you see the same structure, but it's slid over in this direction. That tells us that light is older. The universe has stretched more. And in this one, it's stretched so much that the rest of it is off the page and here again, in this one, it's even. So this one at the bottom was that star that was 13.1 billion light years away that it translates to. The one at the top is only 11.3, relatively close by, right? Yeah, right. So I do this for illustrators. So people say, what is this redshift thing? Well, that's what we mean. We're shifting the spectra over. So you see the spectra looks the same. We just slide it to the right. And there you go. All right. Here's an image in which we're doing the same trick with the spectrograph, except this time we're looking at these smeary structures that you see we've called out in the box sections. And you see the spectra over on the right, and notice they're the same. And so when the astronomer looks at that, the scientist says, that is actually the same galaxy, because the spectra is shifted exactly the same. So here we're seeing gravitational lensing occur. That's not two different galaxies. That's one galaxy that's been lensed to look like two galaxies. Now I'll change the topic, and I'll talk a little bit about planet spectra. If you want to know the spectra of a planet, there's a difference between emission spectra and absorption spectra. In emission spectra, I take some gas, I put it in a glass tube, I put it in a power supply, I send thousands of volts through it, and you get this pretty glowing light, like neon lights like we used to use. Now they're all LEDs. But back in the day when we used to use neon, you get this pretty glowing light. And if I take a diffraction grating, I'll see all these little bands of the light as I separate out the spectra. That's because we're emitting those frequencies off of that. If instead we had some neutral light source behind it, and we have cool gas in front of it, so we're not energizing by sending thousands and thousands of volts through the cool gas, those same atoms will, instead of emitting light at those wavelengths, it will absorb light at those wavelengths. Now, it only does it temporarily. It absorbs the light. If it's the right frequency, it puts the electron into a higher energy state. That electron, it's very temporary. It drops back down to its rest state. But when it drops to its rest state, it re-emits the energy at exactly the same wavelength. The problem is we can't control the direction. So it's just going to go off in some random way. So the energy that comes in also goes out. But since it doesn't go out in the same direction that it was brought in, it goes out in a random direction. To us, we see a subtraction of light. So with the subtraction technique, we can still tell what elements are there. So with that knowledge, we take a star and we measure its spectra. So now we know what the star's got. We wait for the planet here to come in front of the star. And I've got a shaded area representing the atmosphere of the planet. And when that happens, not only does the light generally dim, the light dims and the spectra changes a little bit. And it's that change in spectra that tells us what gases are present, not in the star, but rather in the atmosphere of the planet that passed in front of the star. And that's how we do spectrographic measurement on what is in the atmosphere of a planet. So that's what it does. And so when we do that to, in this case, the planet was WASP 96b. This is the image, right, of WASP 96b. So the image in this case is a graph. In science, we could give you an actual photograph. We could give you a photograph that's been annotated. We could give you an artist rendering, or we could give you charts and graphs, or we could just give you raw data. And so someplace a scientist has to say, what's the best way to get the message across? In this way, they decided the best way to get the message across is not with a photograph of a planet, but rather with the chart graphing out what we found in the data. So we're not giving you the raw data, we're going to chart it for you, but you can see there's several lines here showing the presence of water molecules in the atmosphere of this planet. Now, I think they did do a check on the temperature, and they realized that the temperature is too hot to support life, but it has water molecules in gaseous form in the atmosphere, probably not in liquid form on the planet, but hey, it's there. So that was kind of cool, but we're actually measuring that out of the atmosphere of a planet that's, oh, look, in the lower right corner, 1,150 light years away, and we can tell you what's in the atmosphere. That's pretty cool. So this is actually just a pretty picture that I have, which is, as we were exploring the solar system, I thought I would do this because we did it with Jupiter. The bright thing that looks like a star is actually Triton. Actually, I'll annotate it for you. There we go. That's actually Triton. And you can see some of Neptune's other satellites, but you can also see really cool the rings that Neptune has. So all the gas giants have rings. And so there's another direct image of a planet in our solar system that has rings. Speaking of planets, so this one is kind of cool. You all know what planet this is. But Jupiter is a fast spinner. So Jupiter does a spin in about 10 hours. So they did something kind of interesting. So you see we've called out this region of interest in the graph with the box around the equatorial cloud belt in the image. And then it's these two things that I want to point out. You notice this 1052 value here and this 2055 value there. What they did is at 1052 universal time, they told the telescope to take an image and they zoomed in the camera. And so you can see this orange box here relates to this orange box here. And so you can see each of these has like, there's a little contrasty structure there, a little contrasty structure there. And there's this sort of like Nike swish here. And then 10 hours later, they did it again, 10 hours and 3 minutes later. And they looked at exactly the same three spots. And the idea was, and I apologize because I don't have the numbers, they were trying to see if they could calculate exactly how fast the wind speed was in the equatorial belts. Because you can kind of see this here is probably this structure here breaking apart. This is kind of moved on over to here. And this one, I'm not sure what happened to. That's probably not it there, I wouldn't think. But that's what they're trying to measure, is get samples off of the planet and see what they can find about it. So I thought that was kind of cool that we're able to actually see the motion in the cloud belts using Webb with that. So that's kind of nice. I did also mention direct imaging of exoplanets. So this is a star. And then in the lower inset images that you see at the bottom, you see the obvious 5-pointed star. That's the chronograph of where we're masking out the actual star. And then what you see in the violet, blue, yellow, and red, those are actually images, direct images of an exoplanet around this star. And then you can see the filter names at the bottom, F300M, F44W. These are different filters that the camera is using. I'll show you an example of those here, but it's pretty cool that we're doing direct imaging. The filters, so if I zoom in here, there's F300M, there's F444W. So the W means it's a wideband image. The M is like medium band. You can see the bottom row has N, those are narrowband filters. They have the W2s at the top row. Those are ultra wideband filters on the telescope. And so they've got a filter wheel. Now, by the way, this is just for near cam. The mid-infrared telescope has a filter wheel with filters of its own. This is just the filters on near cam. So this isn't all the filters on Webb, but it has filters of its own. And that's what we're doing, is we're selecting specific wavelengths of light, imaging, seeing what we get, and then translating that into a visible spectra image to create a full color. Yeah. I don't know. I actually don't know if that is. And I don't know if this is, nah, I don't have the ability to pull up the notes. For some of these things, I had notes on them, but I realized that this was added later. It wouldn't have notes. So I don't know the answer to that question. Sorry. I'm sorry? Oh, yeah, the amount of light that it will permit in the bandpass. Yeah, because this isn't the camera. The camera would have quantum efficiency. This is the filter. Oh. So this is the filter, the glass that you're going to put in front of the camera, that's going to decide what wavelengths should be blocked completely, what wavelengths will be allowed to pass, and as Brian points out, how much of the light will it pass, allow to pass. So, okay. All right, so how am I doing for time? Okay, I guess I'm okay. All right, so this is the Southern Ring Nebula. So it looks like the Ring Nebula, but this was taken with NIRCam. You can see the lower right corner of the image. It's 2,500 light years away for this. This is a planetary nebula. So this is what happens when a star roughly the size of our sun, thereabouts, comes to the end of its life and dies. So there should be a white dwarf star no longer active with active fusion going on at the core. And you see this obvious six-pointed star in the middle of the image, and you're thinking, that's our guy. Except, I'll zoom in a little bit so that we can see this just a little bit better. By the way, I love zooming in on these images, and you can see all the crazy amounts of detail, staggering amounts of detail that you can see in this. I've got other images that compare it to what Hubble could do, Hubble's best image of this, and it's just amazing how much more it gets. But this is near infrared. Let me show you what happens if I translate this to mid-infrared. And there you go. It's not one star, it's two. And it's the red one, not the blue one. And so in the near infrared, you couldn't actually see the star at all, which is kind of cool. So there's a demonstration of why would you want to go into mid-infrared. This is one of the other first images that was released. This is called Stephan's Quintet because it's 5 galaxies, right? And so there's a very obvious 1, 2, 3, 4, 5. Except number 5 is actually photobombing. So do you see in the lower right-hand corner, I have 2 numbers, 290 million light years. 1, 2, 3, and 4 are 290 million light years. Number 5 is actually only 40 million light years. That galaxy is actually a lot closer to us than it is to the other 4 galaxies in the image. So that's why I say number 5 is actually photobombing us. But that was kind of cool. And then we can go into Stephan's Quintet. I'll zoom in on this, and I'll translate this into the mid-infrared. And in the mid-infrared, you can see all kinds of cool things. There's a couple cool things. So you can see the 2 galaxies down at the bottom that are clearly well on their way to merging. And then up above, let me better put this in annotation mode. I can't make those go away. Oh, yes, I can. There we go. Okay, up above, you see this region here where gases from the 2 galaxies are interacting and getting heated up, creating this sort of shockwave region that's getting bright and probably forming a lot of stars in the process of doing that. But remember when I told you that when you see the telltale 6-pointed / 8-pointed star, that was actually a star in our galaxy photobombing? And then I said, not always. I'll give you an example later. Well, this is the not always. I'll give you an example later image. This is called a Seyfert galaxy. About 1 galaxy in 10. What that means is this galaxy has an active galactic nucleus. The black hole is having lunch. And so it's devouring matter, and that's what's causing it to glow oh so brightly. And it looks like a star for all the world from our point of view. The other galaxies don't have one of those going on. So like I said, about 1 galaxy in 10 will do that. And they were able to capture that in the mid-infrared, but it didn't show up in the near-infrared. Actually, if I go back to the near-infrared, you can barely see it happening. Let me see if I can, I'll do a done. I'll go back one. And if you look really closely, when I zoom in, I don't know if you can see it. If you look at that image very closely, do you kind of see the star-like rays coming out of the middle? Yeah. It's really hard to see, but it is there. All right. So enough of that. It's probably going to make me do this again. There we go. All right. So this is another one of the first images. They call this the Cliffs of Carina, or the Cosmic Cliffs. This is, again, 7,500 light years away, but this is, again, in near infrared. But I do have an inset where I convert it into mid-infrared. I don't have, what I was hoping to do with this image, and I never did go get one, I always made a point to, is I wanted to go get a Hubble image of the same area of the sky and give you an example, because when you compare what Hubble sees, most of the stars that you see in this image are inside the dust. And you can see it with Webb because Webb can see through dust largely. It can tell the dust is there, but the dust becomes fairly, called kind of opaque, semi-transparent, if that makes sense. Whereas with Hubble, it's just visual. If there's dust in the way, there's dust in the way. You're not going to see it. All right, here's another one. This is the Cartwheel Galaxy. And this is with NIRCam. It's 500 million light years away. We'll go ahead and zoom in on this. And I think I turned this into, I don't remember if I turned this into, no, I didn't, sorry. I'll move quickly through it. It's not one of the interesting ones. Here's the cosmic tarantula. There's got to be another name for the cosmic tarantula. I apologize in advance for not knowing what that is. But you can see there's this really cool star cluster in the center of this gaseous nebula. I did translate it into, I took the mid-infrared and did an overlay for you there. So you can kind of see through it. The other stars largely disappear, but you can see a lot of structures that are in the gas in different wavelengths, the blue and the red. And then this one I did do a comparison of. So this is M74. Brian, do you have an image of this? Have you imaged this before? Yeah. So M74, but notice the middle of it. You see just a crazy number of stars in the core of this galaxy. And what's unusual about this is if I give you a comparison, on the left is Hubble, which is almost as good as Brian's images. On the left is Hubble, on the right is Webb, and in the middle we've combined data from both telescopes to bring out features in both. But look at the left and notice, this is what I said about dissecting what's going on around black holes. It's completely enclosed in dust. You can't see the galactic nucleus of this galaxy in Hubble data. But in Webb data, while you can count every one of the little itty bitty stars zinging around the black hole at the core of the galaxy. So now I'm going to change topics a little bit and talk about a little bit about star birth and star death. So here's some stages of star birth. So you got number one, you got a wispy cloud of gas. It starts to come together. There's all sorts of talks on why it starts to come together. And then you start to get clumps, and those clumps are going to start to form stars, and some of the matter is going to go into the accretion disk, and that can be used to form planets and all the other sorts of interesting things. And the next thing you know, you have a solar system, right? So there's the general idea. But when the star is forming, you've got this pre-stellar region where the star is going to form. It starts coming together, and notice there's this class 0, 10,000 astronomical units, 300 astronomical units, and you start to see a disk form on the horizontal and these jets that I'm showing on the vertical. And then the next thing you know, you get to the end and voila, you've got a solar system. But it's the jets that are kind of interesting. So here is an image of something called a Herbig-Haro object. These are very, very, very young stars. So our star is something like 5 billion years old. We look at stars like, I think Betelgeuse in the Orion Nebula is on the order of several millions of years old. But you generally don't see stars that are only thousands of years old. These are stars that are only thousands of years old. They're not millions or billions of years old. And you see this dusty clump that doesn't make this a very attractive object. But here it is again. This time is imaged by Webb, and now you can see it. So this is a newborn star. And actually, newborn stars are a lot like newborn people. I don't know if anybody's had any, very young children. I don't know how many of you have kids, but you put a 1-year-old and put a plate of food in front of your 1-year-old. And as an interesting science experiment, try to measure how much food ends up inside the child versus the amount of food that ends up on the walls, the floor, the ceiling, everywhere else. The kids are very messy eaters. Well, it turns out very, very, very young stars are very messy eaters. Some of the material ends up in the star. Some of the material ends up on the floor, on the walls, flung all over the place. And so these jets that you see coming out of it are material that the star is throwing away. If I can't zoom this image. It wasn't designed to zoom, but I'm going to try to highlight something if I can. The red stuff that you see here this is a lot of the first matter that was ejected. It's hard to trace, but you can see a little blue filament running along there, and there's another blue filament kind of running along there. if you see those things that I drew. The blue stuff is stuff that the star is only very recently ejected. The red stuff was actually ejected long ago. But again, this is a very young star that is only on the order of thousands of years old. It is not millions of years old. It is hiding inside a dense cloud of dust. And the reason this is significant to science is because it allows scientists to peer into the process of the birthing of a baby star. That is otherwise shrouded in dust, not accessible to us to see what's going on. So it allows us to learn a lot about it. That's why that is an interesting object. This next slide, I want to talk about star death a little bit here. And so on the topic of star death, so let's talk about how stars can die. And you can see on the left, I've got some stars stacked up from really big stars to really small stars at the bottom. The biggest stars can die the death of a supernova. And after the supernova, they might turn into a black hole, or they might turn into a neutron star. More about that in a moment. If there's stars that are kind of big, but not big enough to go supernova, they can leave this thing behind called, they'll turn into a red giant when they finally run out of fuel. The force of fusion trying to blow the star apart finally loses the war with gravity, because while you can run out of fuel for fusion, you never run out of gravity. So in the end, gravity always wins. That thing collapses, shedding off quite a bit of its mass and leaving this thing behind called a planetary nebula. But there's a white dwarf at the core of the nebula. And so I'll show you some examples of that. And then smaller stars like red dwarfs will not become a planetary nebula, and brown dwarfs, you don't even get a white dwarf out of it at the end. All right. Which stars turn into neutron stars is a lot less than you might think. So basically the O-class stars, the monsters, they can turn into supernovas. And the high end of the B-class stars can do this. But most B-class stars don't have enough mass. They don't do that. And nothing else does. So all of these are low mass, and you end up getting a white dwarf. So with that, here's the Ring Nebula, something that probably every one of you have seen through a telescope. What's interesting about this image is one of the guys in our club actually just imaged this and posted it today. And you see these little wispy lines that are coming out of the nebula. And you're familiar with corpuscular rays of sunlight shining through gaps in the clouds. So they're thinking that this is gaps in the structure. I'll see if I can zoom in here. Gaps in the detailed structure here that are allowing radiation to go through, and then gases on the outside are being ionized, causing them to glow faintly as these radiant lines, kind of looking like corpuscular rays of sunlight with that process going on. It really becomes apparent when you switch to the mid-infrared. And boy, are they visible now. And so in the mid-infrared, you can see this. What confuses me about this image is I see these streaky lines out here. I'll do this. I guess I should do it in yellow. This stuff. I don't know why that structure. I get why these structures appear. I don't get why those structures appear. And I didn't get an explanation when they did the training for that. But again, this is 2,500 light years away. This is M57. You've probably all seen it, is my guess. Hit the done button, move on. Okay, and oh, this is a zoom in on the mid-infrared. Okay, let me go over to, this is M1, the Crab Nebula, by our dear friend, Charles Messier, who did all of his telescope observing in the middle of a huge cosmopolitan city before they invented the light bulb. So, and unfortunately, this Thomas Edison guy came across and ruined it all for us. But 6,500 light years away, you'll find this in Taurus the Bull up by the Horns. And you've probably all seen this image. I've seen this image a lot of times. There's something in this image that I'm going to call your attention to that you probably don't see right now. It is here, but I'll go to Webb's view of the same object. So here's the Webb view. Do you notice anything peculiar about the middle of the image? Yeah. It's like, what is going on with all this stuff? So this is actually described as what they call cyclotron radiation. So cyclotron, aka particle accelerators. And the idea is this is a neutron star. So think about what a neutron star actually is. So if you've got enough mass, you've got a star, it's got a lot of hydrogen gas in it. It's got other elements as well, but it's got a lot of hydrogen. To have a hydrogen atom, you've got to have a proton at the nucleus, and you've got to have an electron. The electron stays out here whizzing around. It's mostly empty space, right? If I took a tennis ball and put it in the middle of a football field, I'd have something the size of a head of a pin whizzing around the outside of the stadium, and that would be the electron. The electron is practically nothing, and really, really, really far away. I mean, imagine how many tennis balls you could fit in that stadium. But not a single other tennis ball can get into that stadium because the structure of that atom is preventing anything else from occupying the space. And what keeps it out there is something called electron degeneracy pressure. Well, the problem with forces in physics is you can put a number on them. And so the force is whatever the force is. But when you have gravity, you can keep additively piling on and piling on and piling on. And remember, I showed you this simple equation for Newton's gravity. I can just keep piling on more mass. At some point, the value of F exceeds the value of electron degeneracy pressure. And when you have so much mass that you can actually overpower the atom, you can force the electron into the proton, basically synthetically creating a neutron. And so you've got a star that is basically made up of entirely neutrons. There are no atoms as such that you would find in the periodic table of elements in that star because of the insane amount of gravity. You're one step away from becoming a black hole. Now you have to maintain conservation of angular momentum. So the star is spinning really, really, really fast. And when you're doing this, you're basically putting out a huge magnetic field, and you've got these things caught up in the swirl going around at incredible velocities, just like a particle accelerator. And you're accelerating these particles, and they're now giving off energy. And you can see the energy being given off here by this image that was taken by the Webb. Now, if I go back, well, let me do this. If I go back here and you look really, really carefully at this image, you can barely see some of that cyclotron activity in this image. I've never seen it in any astrophotographer's image. I've only seen it in this Webb image, and I can barely see it. But when you go to the Webb version of the image, it's really easy to spot what's going on here, and we'll zoom in. You can actually kind of see where the neutron star is out there, which I think is kind of really cool. So that is, I've given you some examples of stars being born. I've given you some examples of stars that are dying. This is the point in the presentation where I ask if you have any questions. And the most obvious question that you should all have is, what the heck is that? And the answer is, I didn't Photoshop that in. That's real. And that's from Webb. So the science team found this, and they said, that is so cool, we're going to use it for a Q&A slide. What it is and why it looks so much like a question mark, they actually did give me a slide to show you that this is interacting galaxies. Kind of could make an argument that it's somewhat question mark looking, even though it's not nearly so perfect as the last image. But yeah, so there is the cosmic question mark is out there. It is real. And with that, thank you for your attention. Yeah.
Would it have been more stable to have it at the Lowbrow or Alpine site rather than the
So they put it at the so there's the L1 is closer to the sun. L2 is farther from the sun. Now we do have a number of satellites that are already at the L1 point. They wanted to get it farther from the sun. It actually isn't just parked there. It's doing this weird kind of halo roll thing that it does. And it is, the radius of that circle that it does always keeps it outside the shadow of the moon and also the shadow of Earth. So that was chosen on purpose. But but they're trying to keep it as far away from getting hot as they can. L1 works as well as L2. I'm sorry, but L2 is a little bit farther, so they're getting hit with fewer photons. Excuse me, fewer photons are hitting the shield. Something that I didn't mention that I do talk about in some of the presentations, and I actually have an animation that I can show, is the where can Webb look in the sky? Actually, I sort of have this cartoonish, artistic Webb here. They cannot tilt the telescope relative to those sail-based heat shields that you have. So the whole telescope has to move as one, and that means that if they start to point at something a little too close to the sun, the shield is no longer protecting the telescope. It gets hot, and once the telescope is hot, an infrared telescope, all it can see is itself at that point. It has to cool back down again. They also can't point too far away from the sun. So there's this donut-shaped ring in the sky that is sort of on an axis tangent to the orbit, and it can look at any object anywhere in that donut-shaped region, but it cannot look toward or away from the sun. As it goes around the sun, however, that donut rotates. So it can see anywhere it wants to in the universe. The question is, on what day of the year will it be able to safely see there without heating up? There is one other thing they did. You probably all heard that it got punched in the nose. Its mirror has been struck. So they have modified operations. They used to let the scientists point anywhere in the donut. They now only let the scientists point in the direction that the telescope is moving away from. They don't let it look in the direction that the telescope is moving toward in the orbit around Earth. The idea being that it will still probably have impacts, but they hope that they will be lower velocity impacts by making sure that if there's a high velocity impact, it hits the backside. Yeah. Yes.
How much do they allow it to be angled from retrograde? So like if, for example, if you have the rays coming from here, do they allow the mirror to kind of be like that? So that
oh, it's not that much. It's I'm going to take a wild guess and say it's probably 15 degrees. Maybe it's 20. It's there's a you can all download it. It's free. It's called openspaceproject.org. No, I think it's openspaceproject.com. And it's a planetarium application that you can download. And one of the things that you can simulate with OpenSpace is the Webb. And when you go into all the options that you can turn on and off, there's this thing called it's called the field of regard, but it's unofficially called the safe viewing band. And you'll get this ribbon in the sky, and it shows you from where it is on that date. Anything inside the ribbon can safely be imaged. Anything outside the ribbon cannot. Yep. Other questions?
This would mean that if there was some
if there was some
repeat the question, please.
Event.
Oh, they're asking if you'll repeat the question.
Oh, I just started it actually. If there was some incredible event that was occurring, the Webb may not be able to
Correct.
Look at it when people really would want to in the infrared.
Yes, that is accurate. Now, if there was an incredible event and it was in the safe viewing band, but it was on the other side, it was in the forward direction, they probably would spin it around. But they have no choice to stay within the safe viewing band, because if they go outside of it, the sun hits the telescope, and now all it can see is itself until it cools off again. And also keep in mind, it doesn't image in the visible spectrum. It only so depending on what you wanted to see, it might not be the best telescope for the job.
You have questions from the room? Zoom audience? Whoa,
I put him to sleep.
Okay, last call for questions for Tim.
I have a question.
Yep.
On a microphone, I just talk loud.
Talk loud.
Okay, good. Wonderful pictures. The tarantula, maybe with the Carino ball, the Herbert arrow, and an exoplanet. Those are all in the southern hemisphere. I'm seeing a southern bias.
Well, now, we did show you the northern hemisphere ring nebula. We showed you M57, we showed you M74, and we showed you the Crab. Those are northern hemisphere, and we showed you Jupiter. I mean, you got to give us that.
There is no bias. It points.
Correct. It does point in all directions. Yeah, they can point. They can always point. So if you think of a tangent to the circle, they can point in any direction tangent to that, up, down, backward, forward. They just can't point toward the sun or away from it. They have to wait for the telescope to rotate to where that becomes the direction. The good news is most things in, unlike sports photography, they talk about in photography, they call it the decisive moment, right? You got to capture the exact, the guy's sliding into home plate. You got to get it right when he's just about to be tagged out. You got to get the decisive moment. In astronomy, most of these things will be here in 3 months. So if you can't shoot it today, you still probably didn't lose your chance. That's not always true, but for a lot of stuff, it is true.
Okay,
All right.
thank you very much, Tim.
Thank you.
And as a humble token of our appreciation, we'd like to present you with
Oh.
an official club
I
t-shirt.
get a t-shirt.
Yes.
Do I get a slimming diet to go with it?
No, that's what I get.
Thank you very much.
You're very welcome. Thank you.
Thank you.
Much appreciated. Okay. On with our officers meeting. I just got a couple of things. First, we do technically have a open house scheduled for tomorrow night. There was some confusion really because the date had changed. I think we told the observer the date changed, but not all of us knew about it, including me. So, but as it turns out, we don't have enough people really to operate the thing anyway. Kind of like we don't have a map operator. Well, maybe Dimitri, but I don't think you want to do it by yourself. Thank you, Tim.
If I watched you guys do it, and if you guys, I've seen, like, I watched you guys, take it out and put it in, I think, 3 times now. We obviously didn't start to look like they feel confident in doing it. I would be willing to, if they feel now, and if they don't, then obviously.
Yeah, we'd have to get you a key, but then I'm concerned that there maybe be you and maybe one other person, and that isn't going to be enough. So, yeah. Exactly. Exactly. Correct. Yeah. Right. That's what I'm thinking. Maybe the best thing to do is we cancel it for technical reasons. So, okay. I also wanted to mention, I'd mentioned this in emails, I put out a call for speakers because we're about to run out of them. And whoa, did the club ever respond? Do you need this microphone anymore? I'm just hearing myself through here, I guess, so. Pardon? Yeah, okay, that's true. So anyway, it turns out that we went from 0 to 100 very quickly. We have speakers for the rest of this year, which is only 1 month left anyway. But in January, we have a woman that has just graduated from EMU that is going to talk to us about space weather forecasts and how to catch aurora in your backyard. Then we have, I'm sorry, she is from the U of M, I believe. Our February speaker is from EMU, Rosie Friend, and she's going to talk about atmospheric gravity waves and solar eclipses, 2 rather different. Well, we'll see. Are they related? March, we have Jim Shedlowski coming back, who's been a pretty regular speaker for us this time about searching for the dark universe. And then, and I thought this was really cool because at the same time, as you know, the officers want to do a survey to see what people thought of the club, what they'd like to see the club do, et cetera. And Brian Autumn, who was very convenient, professionally does such things, sent that survey out. And a couple of things in there were about some variety in our meeting topics and how people like some kind of hands-on things, a lot of things with their own club members. And it just so happened simultaneous to that, we had Jeff step up, and he is going to in April do a topic on automated astrophotography on the cheap. And then that's followed up by Gary Nichols, who's going to do a presentation on the new electronically assisted telescopes. I think you're covering 3 of them. Yeah, and some of the pros and cons of each one. And depending on what he says, I might just make a motion after that the club purchase a C-Star unit. So, but we'll see. And then something that's kind of new in June, and this was an idea that Brian came up with, and it seemed to be kind of popular, and that was a showing of people's astrophotography, but we're only giving you 10 minutes, strictly enforced. We even thought of making it like a little gong show thing. Does anybody have one of those stage hooks that I can reach for people? But anyway, so I've just now, lacking a better thing to call it, is timed showings of astrophotography, 10 minutes and you're gone. And we do have 7 people lined up to participate in that. Ed Hernandez says he only needs 5 minutes, so he should escape the hook pretty easily if he sticks to it. But this might be fun. And I think it's something, if everybody likes it and it's very successful, maybe we'll do another one and find some way to make it more interesting, like a competition, some prize to be given out. Who knows? We could have some fun with it. September meeting is going to be canceled because this year it conflicts with Astronomy at the Beach, which it does do every so often. So we're just canceling that one altogether, which makes it real easy to find a speaker for that one. And then I forget who floated this idea out there when we were having the meeting about the survey results from Brian. And that was the idea of having a picnic, which also kind of came out of some things that we saw in the survey too. So in August, we're going to have a club picnic. We still have just the initial thoughts on where and that kind of thing, but we thought that might be fun. So another one will be easy to get a guest speaker for, huh? Because it'll be us. Anyway, that just leaves us July, and I assume that we're going to be back over at EMU, but I'll confirm that with Norb. And might just well be again that Norb will be our presenter there. And if that's the case, that just leaves us 3 months left next year to fill out. So again, talk about going from being worried about guest speakers to having an abundance. Wow, I was really, really proud of the club. And then
Charlie, I can confirm that we'll be okay for July.
Got it. Oh, you are third Norb. Okay.
Yeah.
I didn't see in the audience. Thank you. Appreciate that.
As far as the subject's concerned, we'll TBA that for the moment.
Right. The one thing we do know is we will have pizza and cookies and all that again. So
Yummy.
that's a very, very fun meeting over there. And then you noticed I had mentioned several times the survey that we ran, and I'm done with my part. So when I call on officers, I'm going to call on Brian first, who is taking the minutes for us tonight also. Thank you very much. To give us some more detail about that and a couple other things he has over here. Turn it on, see if it is. I'm not sure. If not.
Thing 1, 2, 3. Hello. Nope. So turned on. But I'll just use that.
I can get it on the phone. Here.
We'll just make this quick.
Yeah.
I want to thank everybody for taking part of the Lowbrow survey. We got 86 people responded in our survey. It was fantastic. Thank you, everybody. That was really awesome. And we learned a lot. And there's going to be a report. We'll put it in the newsletter, and you'll be able to learn, and what we learned. But we're really excited about that. And just a top line is that people are happy with the club. And there's no one thing people like about the club. They like a lot of different things. There's a lot of reasons that people join, a lot of reasons they stay. And so that was really good. And then we got some ideas, some new things that like we talked about, and we're trying to implement. So we're really trying to use the responses that people gave. And then we also are trying to address maybe some of the things that people thought they weren't so excited. The only things they weren't so excited about, some people say, maybe there's a lot of emails. So we might work on that, and then
So we might work on the emails, and they're just trying to be more welcoming and to get new people involved and get them into the club as fast and as easy as we can. So we're going to work on those things. So we're gonna have a report probably in the newsletter and make things available for folks. And I'm available for any questions if anybody wants anything deeper tonight. Thank you. Thank you for participating.
You want to mention yourself over there?
Oh, I brought a free book, The Science of Interstellar Movie. Okay, it's a great book. It really gets into the relativity and the black holes and stuff. The latter half of it was still over my head, even though they had like nice cartoon pictures. And then I have some of my calendars if people want a calendar, and I got some pictures of the sky that I'm letting go. That's it.
Thank you, Brian. Oh, and before I forget, I did have one other thing just to remind people that we do have the observatory running at the same time right now, and it is clear out tonight. So if anybody's interested in taking a little tour up there, Austin is going to be coming in toward the end of the meeting. So just kind of hang out, join up with him, and we'll take you up there and show you the stuff. So, Dave.
Okay, so December 2nd, Brad Adams, in the beginning of Saturday morning physics talk, formation of planetary system. Oh. Does that work? Okay. So December 2nd, Fred Adams will be giving a talk, Formation of Planetary Systems, Saturday morning, that's 10:30 a.m. Weiser Hall, 170 Weiser Hall. Charlie, you forgot one. On December, the speaker will be David Gerdes, who he's the chair of the physics department. A lot of his research involves astronomy related stuff. So, and he's a good speaker. So, Debbie Smith thought of asking him. So that's mainly it. I probably should mention that Amy Harris, who's been the director of the Museum of Natural History, retired. I did have an opportunity to talk to Dawn Johnson, who's the interim director. So we've done some collaborations with the museum in the past. And if there's interest, we could do something like that in the future. They have a nationwide search for a permanent director. And when I asked Tim, how long is this going to take? He said, a long time. So we have no idea how long it's going to take. So that's it.
Observatory Director, Jack Erskine.
All right, basically, we're getting ready to move the 17.5-inch telescope to figure out if we're going to leave it in the observatory. We used to put it over at Dave Jorgensen's, but now that he has passed, we did discuss this once before about maybe putting it in a storage unit for like December, January, February. So we're just working on that right now. The other things, like I said, I discussed the last time, we did put the fans on the mirror to get rid of some of the temperature problems and that. Other than that, I don't have anything really else to talk about with the observatory right now. I'm just going to get ready to do some more maintenance on it for the winter and that coming up. So with that, I'll turn this over to our next.
And our online coordinator, Jeff.
Yeah, you can't get rid of me. I guess there's one announcement we had for our new WordPress site. Work continues on migrating stuff over, but I met on Sunday with our member Barry Chapman. he works for Volkswagen, and he has an agency that does WordPress sites for all kinds of places. And we sat together, went through our website, and found some places where some of the tools that his agency uses and licenses could be very valuable in doing things like some of the online profiles that we've discussed in the officers meeting and here, better use of the screen space, better looking themes, menus, etc. A lot of customization, but the tools, of course, cost money. And he's basically going to do a database dump of our site, import his, and do kind of a mock-up to say, you know, what he could do for us in alternate hosting. Right now, we have a 3-year contract with this HostGator, which apparently is, it's cheap, but it's not the greatest firm in the world. He's got all the services they offer, and it would be possible to use his stuff. So we're going to wait and see what that looks like, and see if there's could, you know, do some nice things for us, perhaps even solve some of the email and digest issues and stuff. The other thing that happened just recently, and that's courtesy of Tim from Monday night's GLAC meeting. Yeah, he's surprised, like, what did I do? He pointed out that our Astrospheric license, we have, if it's a astrospheric.com, or there's an iOS or an Android app that you can get. And if you register in the subspace portion of it as a member of the University Lowbrow Astronomers, that's the formal group, then you get access to the pro version. And up until, what was it, Wednesday or Thursday, this feature wasn't actually enabled because we hadn't completed the third step. Wednesday night, I went off and did that. You'll notice that there's an Astrospherics section on the old website right now. And with that, we got approval, and now all members who sign up for that are able to get the pro features of Astrospheric, which includes 2 additional sky models for the clouds and whatnot, and additional days of the forecasting. So I enabled myself, and we've got, I think, 3 or 4 other members, officers, who can get you signed up or approve it, whatever. But basically go to that subspace, get us to, there's a code that you need to sign up with the group. And after that, you got full pro access for free. So a member benefit.
Like, I've got it loaded on my phone. How do I get over to the pro? Because it wasn't pro before. But I did log in, I believe, as.
If you look in right now, mine switched over as soon as they did it, and it'll just enable that. So if you've already signed up and you're in the registry list,
Okay.
It should be good.
I thought I might have seen something new, but on the other hand, I also saw a thing that said about going pro. And I thought, well,
Yeah.
why am I seeing?
Yeah, you in the past you've seen that, but I would recheck it again.
Okay. All right.
You were going to say, Tim? Yeah, as long as you're in that lowbrow registered
Which
group.
I think you're showing me is in, right?
I
it
believe
said
you
that,
were
yeah.
in. I think you're one of the admins
Yeah,
too.
that's what I thought.
Yeah, but if you check the app right now, it should come through.
Okay.
I did confirm that we only need 20 members to be registered for that feature to go through, and we have 41, so we're well over that limit. But that was a big news. Register if you have problems, just, you know, email the officers and we'll figure it out for you and get you that. But it's a really nice program. It's one of the best. It's one that I use all the time for figuring out whether I'm going to do anything. So I think today it was 18 and 23 or 19 and 23. What does that add up to be? 19 Zoom max.
In person 20. Okay, I had 22 or 23.
Yeah, 23.
And I had 19 in Zoom. Yeah.
19 Zoom. Okay. So whatever that adds up to be is like 52 total. And Dimitri.
So I heard
Astrospheric.
The basic version is free, but then you ought to get automatically get the paid version.
If you go to the subspace tab and sign up as a member or request it or whatever, it'll probably ask for a code as well. And I can have my computer up and do the code later. Yeah.
Nobody has to review the preview.
Right.
And it's just the weather, right?
Yeah, it's a cloud watching.
Well, it's got stuff besides that, but that's primarily it, yeah.
It's a very rich app, and the website, the app, they all work the same. They look great.
It updates, the main models are updated once every 6 hours on each particulars. The national weather models is updated every single hour. That model, however, only gives you forecast for 6 hours in the future. Then it's 12 years. And then it gives you one model for 10 days, but that's not accurate.
Hope everybody caught that on the microphone. I was pointing it that way, so.
It does other things. It's going to be an ISS mass, Campbell ISS icon, up into the sky.
Yeah, I forgot about the ISS stuff.
Yeah.
I realized that this, even though I said it was clear, I don't know the sky is over.
Yeah. What was the other few? I also set it up for, I have a number of viewing locations that I go to regularly, and you can put in different lat longs for your various places that you go. So like my father-in-law's places up in Midland, I put that in there. So when I'm up there, I can check on what the weather's going to be up there. So it's a really nice app, and I'm so glad that we got it up to the pro level, because it gives you a lot more information. I think that's all I got.
Back to you, Charlie.
Okay. We have 2 more officers in the Zoom audience, so I will ask Jim.
Not a whole lot. The picnic is something we were doing when I first joined the club, and it suffered from meager attendance, mostly because August is when most people can get out of town. The university summer session is over by the 3rd Friday, and so before that first football game, there's nobody in Ann Arbor. But it's 15, 18 years later, so, and we do have a dearth of social interaction in the club because of COVID, and some of us not really being comfortable in crowds or in close quarters with folks that have been who knows where. But outside of the picnic, that would be a great addition to the club activities. What we need is to do some brainstorming about where to have it. That picnic 20 years ago was at Hudson Mills. The main thing we thought of is that the weather isn't always the best on the day you want to have your picnic, so we would need to have a shelter, a pavilion, so that the picnic could go on rain or shine. So I guess those of you out there that have ideas about where to do this, that so we're not driving 50 miles, should send them in, and we'll figure it out. And also whether you actually want to do it. I mean, this is something, we should have some idea of, there'll be some attendance. I saw one thing in the chat that, at least one of you is ready for a picnic, so hopefully a whole lot more of us are. The other thing about the 17 and a half, Judy Jorgensen did offer her, Dave's workshop, but we haven't talked to her since his Memorial Wake this summer, so I don't know how to contact her if anyone does, or maybe Dave's old email will work, but that is one place we might be able to take the telescope. And that's it.
Thank you, Jim. And we will move to our treasurer, Doug Scoble.
Hello there, can you hear me?
Live from Traverse City.
I see some nods, okay. good to join a meeting for a change. So just a couple things. We're still holding at 201 memberships, I should say. Pretty good. As far as expenses the past month, $75 and some change to Jack for the fans on the McMath. And then we bought a Zingerman's gift card to Brian, who was the October speaker. And other than that, it's just a couple little bits, you know, the newsletter, we're only sending 3 of those out now. We've been phasing it out, and so that's a very small charge. And then the monthly $16 or so for the hotline, the AT&T hotline for open houses. So other than that, the only other thing is the RASC calendars and handbooks. We still have 9 calendars and 7 handbooks available for folks to order. And if anyone's at the live meeting, Dave Snyder agreed to collect money if someone wants to pay in person instead of PayPaling or sending a check in the mail. You can hand your money to him if you'd like, and just make sure he knows what you ordered and how much money, and he'll make sure the money gets to me. So that's everything I have right now.
Okay, thank you, Doug. Does anybody have anything else?
Oh, I would add one more thing. You're talking about the 17.5. I would recommend keeping it in a heated space, or at least, you know, keep it above freezing. The batteries and such. You know, Dave's workshop was great because I think he kept it around 45 degrees or so in there through the winter. I think the observatory, I think the fluctuating temperatures and how cold it would get in there, I don't think that'd be good for the scope. So if you can find a warmer place for it, I think that would be good.
Thank you.
Charlie, I have a comment for Doug.
Yeah.
I
Doug
wanted
Washoe
to
on
mention
there?
to you, Doug, that your 16-inch telekit was a success with one of my observational students at Fish Lake this past weekend. And Rosie still enjoys use of the 18-inch Blondie from Mark Depressed. So both scopes were not far from each other at Fish Lake. And we had 3 beautifully clear nights for November. This is unprecedented. Not only was it relatively mild, but clear 3 nights in a row in November is unheard of. And here we are again tonight. So
yeah.
Thank you.
Well, I'm glad it's working out well for you.
Thank you.
And I've converted it to a big screen TV and a high-end sound system in my new man cave in my basement. So it sounds like a win-win.
Good.
Anybody have anything else? Do I hear a motion to adjourn? So nobody wants to leave, huh? Support? And Doug, go ahead and oppose it. You always do. He's not going to either, so I guess we're adjourned. Happy Thanksgiving, everybody.
Is he here? I don't see his name.
Peace.
Anyway. All right. Good night, everybody.
Good night, everyone.